Okay, so welcome to Math 389. 383. This is lecture 26. And so what I want to do today is I want to talk about continuation of the Riemann zeta function. And then depending on how much time there is, we'll talk about some other related items. All right. So the first is there's a lot of different ways to prove the continuation of the Riemann zeta function. Not surprisingly, different methods use different amounts of information. Whenever you have calculations like this, you always want to ask, what is the source of the miracle? Why were we able to do this? How far do we expect to push this? Do we expect this to generalize in other settings? So it's very easy to just follow algebra line by line by line. You want to try to step back, look at the big picture, and get a sense of why is this able to work. Okay. So the first is, some links. If you want to be a professional mathematician, especially if you're considering number theory, at some point in time, you should read Riemann's original paper. And so I will post some links to it, although if you can't find it in the 21st century with a quick web search, you do not deserve to continue on in mathematics. This is not that hard to find. Here is the here's the original. And so the Riemann hypothesis is buried in this. The English translation, for those of us who do not speak German, I can only read mathematical German, is towards the end. One now finds indeed that approximately this number of real roots within these limits, and it is very probable that all roots are real. This is essentially writing the roots as 1/2 plus I gamma, and then saying that gamma has to be real, that all of the zeros in the critical strip, real part of S between 0 and 1, which we'll talk about more later, they all have real part 1/2. Certainly one would wish for a stricter proof here. I have meanwhile temporarily put aside the search for this after some fleeting futile attempts, as it appears unnecessary for the next objective of my investigation. That's the Riemann hypothesis, just put in as a casual remark. Wouldn't it be nice? It's kind of symmetric. Wouldn't this be ... Now, what was Riemann trying to do? He was trying to count how many primes are there up to x. And so if we knew things about the distribution of zeros of his function, it turns out that by using the tools of complex analysis that we've developed, you can turn this into a proof of the prime number theorem, that the number of primes up to x is about x over log x. Now, if we want to just do a quick rough heuristic as to why this should be the case, it's not so bad. If we want to prove it rigorously, we need some additional properties of the Riemann zeta function. So if you take an advanced course in analytic number theory, they would prove all of the additional stuff you need so that you could have a complete proof of the prime number theorem. If we want to just see that it's reasonable or that it's a consequence of some assumptions about the distribution of zeros of the Riemann zeta function, that's a lot easier, and that's something that we can do. And so the goal for us right now is to just give you a sense of why we're spending so much time learning all the stuff that we're doing. What are the applications? And it turns out the more we know about the zeros, the more we can say about the primes. It's also worth remarking that a lot of the results in complex analysis were proved by people trying to understand how many primes there are, what are the distribution between prime numbers, is that this was all tied to the Riemann zeta function, and this was the inspiration for a lot of the development of the theorems that we're seeing. All right, so the first thing is where can the Riemann zeta function be 0? And so remember that the Riemann zeta function is defined as zeta of s is the sum n equals 1 to infinity of 1 over n to the s, which is the product over primes 1 minus 1 over p to the s inverse if the real part of s is greater than 1. So while this initially only makes sense when the real part of s is greater than 1, we will see later today how to extend this to be a valid function for all of s. This is something we've already seen when we looked at the gamma function, and this was one of the reasons why we studied the gamma function earlier. We initially have something that was defined when the real part of s was greater than 0, and then we saw a way to extend that definition. So we can similarly do the same thing here. It turns out that by looking at this product definition, we can prove that this product is never 0 if the real part of s is greater than 1, which means that the Riemann zeta function can't vanish when the real part of s is greater than 1. It's actually not so bad to show that the Riemann zeta function can't vanish if the real part of s is greater than 1 if S is real. Can anybody give me a proof that it doesn't vanish for real S greater than 1? And feel free to just put it in the chat. So why do we know that this can't vanish if the real part of S is greater than 1?
This is from Zoom. I have
Yep.
just because the sum 1/p to the s converges absolutely, I believe, because the p-test.
Okay. But we need a little bit more as to why do we know it can't ever be 0? So I agree that it converges, but could it converge to a 0 if the real part of S is greater than 1?
Each prime is greater than or equal to 2, and then it's even larger when raised to s in absolute value. So
Well, but we have a sum of 1 over n to the s, right? Or we have a product of 1 minus 1 over p to the s inverse. Why do we know that this? I'm sorry?
Yeah, can we argue, because we know that like the infinite product converges to 0 if and only if one of the term is 0. So can we just argue that none of the terms in the product is 0?
Well, we like to talk that way, but I mean, I could give you products where each term is going to 0 and the whole product will go to 0. So I want to be very careful about using a result like that. You're looking at this at too high of a level. Prove to me, you can either look at the sum or the product. I claim one of them is easy to look at to show that it can't be 0 if the real part S greater than 1 is real. I'm not saying for all real part of S greater than 1. I'm just saying if S is a real number greater than 1, I know that one of these has to trivially be non-zero.
the sum.
Good. Why does the sum have to be non-zero?
Because these are like positive numbers added to one another.
They're all positive numbers, right? So since they're all positive numbers, there's no way that the sum can vanish. So we know that the sum can't be 0 if the real part of S is greater than 1 and S is real. The trick is, well, what if S was complex? Could it cancel then? And so I'll leave that as an exercise to you to prove. I will show you that the sum converges without using calculus. So you had mentioned P series, and P series is using calculus to replace this with an integral. And I want to do this proof because it illustrates the dyadic decomposition technique which we saw last time. So we can write the interval, whoops. Sorry, we just had an extreme close-up. Okay, so we can write the interval 1 infinity as 1 to 2 union 2 to 4 union 4 to 8 union ... We can do this as a dyadic interval. So this is going to equal the union of 2 to the n to 2 to the n plus 1. N goes from 0 to infinity. And now let's look on each interval. On the interval 2 to the n to 2 to the n plus 1, we have 1 over n to the s. Can somebody give me an upper or a lower bound for 1 over n to the s on this interval? And so actually I probably shouldn't be using n here. Let me use a different letter. Let me use k. And so here we're going to be looking at all n in the interval 2 to the k to 2 to the k plus 1. So can someone give me an upper bound or a lower bound for 1 over n to the s?
Wait, do we assume S to be real?
No.
Then shouldn't we put
Sure. Let's put absolute values, yes.
Yeah.
So then it's like 2 to the minus k and 2 to the minus k plus 1, or some like loose bounds, or
almost. So which is the upper bound?
One over 2 to the ks.
Yep. Because each term is going to be greater than or equal to 1 over 2 to the k. So when you divide, it goes in the opposite direction. And the lower bound is 1 over 2 to the k plus 1 s. Okay. Now, if you look at the lower bound, for the lower bound, we also have a 2 to the ks in the denominator, and then we have an extra 2 to the s. So I can just put over here a 2 to the negative s up top. So notice that the upper and the lower bounds are almost the same. For fixed s, the upper and lower bounds differ by a factor of 2 to the negative s, which is fixed. Okay. So really, the point here is on these dyadic intervals, there really isn't that much of a change in the size of the function. So when we're looking at 1 over n to the s, it's changing by at most a factor of 2 to the minus s. Now, how many integers are there between 2 to the k and 2 to the k plus 1?
Two to the k.
2 to the
2 to the
k.
k. So the sum of 1 over n to the s is going to be less than equal to the sum. K will go from 0 to infinity. And then we have 2 to the k elements. And each element is going to be at most 1 over 2 to the ks. So that will be a sum. K goes from 0 to infinity of, now what will we have? We'll have 1 over 2 to the s minus 1 to the k. And this should be absolute value here. Yes? I'm just bringing the 2 to the k downstairs and then just pulling out the k. As the real part of s is greater than 1, the absolute value of 2 to the s minus 1 is equal to 2 to the real part of s, which is greater than 1. So geometric series with a ratio less than 1. So it converges. So this is a simple proof that the sum converges without using calculus. And again, it's always nice to get a sense of how deep is a result. We do not need to use calculus to show that these p-series converge. And in fact, we can get a pretty good estimate of upper and lower sums by seeing that they don't change by that much. Okay, so the next result is one of the most important in all of mathematics. So this is the analytic continuation of the Riemann zeta function. So we start with the function zeta of s. And then what we do is we take zeta of s and we multiply by a bunch of factors. We multiply by 1/2 s minus 1 gamma of s halves pi to the negative s halves. Some of these factors matter, some of them don't. The ones that matter are the ones that have an s in it. The factor of 1/2 doesn't really matter if you put that in or not. You can have slightly different conventions in terms of what do you want, how do you want to normalize things with constants and everything. And this function turns out to have the remarkable property that when you evaluate it at s, that equals the value of this at 1 minus s. And we're going to see that there's a way to write this function as an integral that makes sense for all values of s. And because of that, we'll then be able to express things everywhere. Okay, so let's start with some preliminaries. We're going to try to find first a cheaper way to extend the zeta function to make sense for more values. So I claim if you look at zeta of s and you subtract 1 over s minus 1, it's equal to the sum of the following. So we have n to the minus s minus an integral from n to n plus 1. And again, you always want to be careful to make sure things converge. And we're going to be okay if the real part of s is greater than 1. And if you look at what's going on here, the first part, the sum of n to the minus s, that's just the zeta function. For the second one, the integral of x to the negative s, well, we just integrate that and we'll get x to the negative s plus 1 over negative s plus 1. When we sum, we're going to have the integral now going from 1 to infinity. And that's going to just give us the 1 over s minus 1. So when you just do the integration out and just put all the pieces together, you get that this is just the same as zeta of s minus 1 over s minus 1. Why are we doing this? Well, as s goes to 1, what happens to the Riemann zeta function? Oops, I went the wrong direction. Now, zeta of s is the sum of 1 over n to the s, and goes from 1 to infinity. What's the limit as s goes to 1 from above? The plus sign means from above. What does that equal?
It diverges, no?
It diverges, so this is going off to infinity. And so this is why we subtract 1 over s minus 1. This is a pole of order 1 at s equals 1 with residue 1. So in mathematics, if there's some information you have, if there's some knowledge you have, you try to subtract that out and then look at what's left over. We know the zeta function is blowing up as s goes to 1. And with a little bit of work, we believe it has a simple pole of residue 1 at 1. There's reasons to expect this. And so we think it might be a good idea to subtract off 1 over s minus 1. And that this new quantity might be nice. And if this new quantity is nice, then we can write the zeta function as 1 over s minus 1 plus something nice. Oh, okay, there's our pole, and then the rest will be holomorphic. And the reason we're breaking the interval into intervals of length 1 from n to n plus 1 is we can now combine everything. I can write n to the minus s as the integral x goes from n to n plus 1 of n to the minus s dx. And the reason is the integrand is constant. And the length of the interval from n to n plus 1 is just 1. So this is just a fancy way of writing the number n to the minus s. But by doing this, I can now combine the n to the minus s and the x to the minus s and integrate that from n to n plus 1. Now, if you look at this, when x equals n, the difference between the two is 0. And when x goes up to n plus 1, the difference isn't going to be that much. And that's what we're doing over here, is we're trying to figure out how much of a difference can we have between these two numbers. So what's going to be the largest difference? Where do you think, what value of x will be the largest difference? So the largest difference should occur at the very end, when x equals n plus 1. So one possibility is you could just say, let's estimate this integral by taking the worst possibility at every moment. Okay. That's one possibility. The other possibility is let's try to analyze n to the minus x to the s. And so it turns out if we
Professor Miller, I think we couldn't hear you. Oh,
I'm sorry.
yeah. I think previously we couldn't hear you.
Yeah, no, we could-
Okay, sorry. So I was just saying that we could try to estimate the integral by looking at the worst possibility. It's closest when x equals n, the difference is 0. It's furthest when x equals n plus 1. And we could try to see what's the maximum distance, put in that maximum distance everywhere, and see what you get. We could also try to be a little bit more clever and see, well, just how far is it for each choice of x? And so if I want to look at n to the minus s minus x to the minus s, I claim it's equal to this integral. And the reason is if I integrate y to the negative 1 minus s, I increase the exponent by 1, so I get y to the negative s over negative s, right? I might have a typo somewhere,
Yes.
but, and then I evaluate this at n and x. And so I would get, the negative sign is going to flip the order. And so I'd get n to the minus s minus x to the minus s. And I would have a 1 over s outside. So I think I actually have a typo. I think it's a 1 over s, not an s.
Well, you have an S on the outside anyways, so it will cancel.
Right, but good, right. That s is going to multiply by this s and cancel. Good. And that's why it's equal to n to the minus s minus x to the minus s. Good. And so now I claim that this is just less than equal to the absolute value of s, which is outside, and then n to the -1 minus sigma. And so how would we get n to the
Wait, what
-1
is
minus?
sigma? Here?
Sigma is the real part of s.
Okay.
And so when we look at this interval, the largest the integrand is when y equals n. Because the larger y is, then the bigger the denominator, so the smaller things are. So integrand is largest at y equals n, and the length is at most 1. So the integral from n to x of y to the -1 minus s dy is going to be less than or equal to the maximum value, which is n to the -1 minus sigma, times the length of the interval, which is 1. And so when we put all this in together, this yields the sum, n goes from 1 to infinity of the absolute value of s. Then we have 1 over n to the 1 plus sigma, and this converges as sigma, which is the real part of s, is greater than 0. So this is a short, simple proof that we can extend the Riemann zeta function. So we can now write zeta of s. Put this in red, it's so important. So so we get zeta of s is equal to, I'll do it as the sum, n goes from 1 to infinity of n to the -s minus the integral from n to n plus 1 x to the minus s dx plus 1 over s minus 1. And what must be true? As long as the real part of s is greater than 0, this makes sense. So initially, the Riemann zeta function only makes sense if the real part of s is greater than 1. When we look at the sum expansion, we need the real part of s to be greater than 1. But when we write it like this, we're pulling out over here the blow up. So pulling out the blow up at s equals 1. And that's why this piece over here is now okay if the real part of s is greater than 0. Before, we needed the real part of s to be greater than 1. But now that we've pulled out the blow up, this sum is going to be well defined as long as the real part of s is greater than 0. So this is the first continuation of the zeta function. So I want to do another continuation now. And this is going to use what's called the Dirichlet eta function. And so it's very similar to the Riemann zeta function. What's the only difference? We have a -1 to the n plus 1. So if I write out the zeta function, so zeta of s would be 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s, and so on and so on and so on. And of course, we need the real part of s to be greater than 1. And then eta of s would equal 1 minus 1 over 2 to the s plus 1 over 3 to the s minus 1 over 4 to the s plus ... And again, initially, maybe real part of S is greater than 1. We know that'll definitely work. But because it's alternating, maybe it works for better. Maybe can do better. When you see these two expressions, what do you want to do? Add or subtract, something like that. And so it turns out it's very useful to look at a combination of the zeta function. So if we look at 2 to the 1 minus s times zeta of s, this is 2 over 2 to the s times zeta of s. Well, the 2 to the s just means replace all the denominators with twice their value. So we're only going to just get a zeta function with just the even terms. And the 2 just means we multiply everything by 2. So we would have 2, and then we would have 1 over 2 to the s, plus 1 over 4 to the s, plus 1 over 6 to the s, plus 1 over 8 to the s, and so on. So we've seen this trick before as well, that just, if you have, sums over the evens, if things are nice, you can pull out a power of 2, and then you just have the whole expression again. So now, if we look at zeta of s minus 2 to the 1 minus s zeta of s, well, we don't have any odd terms. So in the 2 to the 1 minus s times zeta of s. So all the odd terms survive as before. So we have 1 plus 1 over 3 to the s, plus 1 over 5 to the s, and so on. For the even terms, zeta gives us a 1 over 2 to the s. We subtract a 2 times 1 over 2 to the s. So we're left with a minus 1 over 2 to the s. When we look at what happens with the 4 term, zeta gives us a 1 over 4 to the s. We subtract 2 times 1 over 4 to the s. We have a minus 1 over 4 to the s. What function is this? It's just our function eta of s. And so we get zeta of s times 1 minus 2 to the 1 minus, 1 minus s equals eta of s, or zeta of s is 1 minus 2 to the 1 minus s inverse times eta of s. So a couple of things to note. So the first, prove eta of s converges if the real part of s is greater than 0. It makes sense that there should be better convergence properties because we have this alternating signs. We've got to be a little bit careful because s is now complex and it's not just real valued, but there's this alternation of signs. So if this is true, we now have a function that makes sense for real part of s greater than 0. This gives us an extension of the zeta function. Do we know any troublesome points for the zeta function?
1.
1. And so what should happen to the zeta function at 1?
Diverge.
It should diverge. Now, let's look at what's going on. Can anybody tell me what is eta of 1 equal to? So this would be 1 minus a half plus a third minus a fourth.
Log 2.
Yeah, it's
It's
like
just the-
ln2.
It's just the natural log of 2. So what must be true about 1 minus 2 to the 1 minus s? What should be true about 1 minus 2 to the 1 minus s as s goes to 1?
0.
0. So how would you evaluate the limit as s goes to 1 from above of 1 over 1 minus 2 to the 1 minus s?
Probably like rearrange it somehow and do L'Hopital.
So we'd love to do L'Hopital. So I can't yell at you for thinking that because that's what I want to do as well. But why can't we use L'Hopital?
Well, because
because
it's
the
like 1
numerator
over
is
0.
not
Yeah, it's
independent.
not 0 over 0. So what we can do is we can say this is the limit as s goes to 1 from above of 1 over 1 minus e to the 1 minus s log 2. And now that's the limit as s goes to 1 from above, 1 over 1 minus, and then you're going to get 1 minus 1 minus s log 2 plus dot dot dot. And now the ones cancel. Did I get things wrong? I'm just wondering if I'm off by a minus sign somewhere.
Oh, I think the Taylor expansion for e to the x.
Oh, good, good. That should be a plus
There
sign
should be
here.
a plus.
Yes, that should be a plus sign here. Good. And now when I expand, the negative is going to convert the 1 minus s to an s minus 1. We'll get s minus 1 log 2 plus higher order terms. Ah, good. And when we multiply by the natural log of 2, that's going to cancel, and it's going to look like, 1 over s minus 1, 1 over natural log of 2. And then the natural log of 2 will cancel. And so this is going to be giving us the same pole as before. We're going to still get that the zeta function is going to look like 1 over s minus 1 when s tends to 1 from above. So it's always nice when you can prove things multiple ways. I would love to do L'Hopital here, but it's not exactly of the form for L'Hopital. We could multiply by s minus 1 to try to find the pole. And then we could use L'Hopital. So as an exercise, you could consider the limit as s goes to 1 from above of s minus 1 over 1 minus 2 to the 1 minus s. And now you could use L'Hopital. And that would be another way to see that this is going to look like 1 over natural log of 2. Okay. So moving on. Let's just briefly look at the following. Can anybody tell me what 1 plus 2 plus 4 plus 8 plus 16 plus 32, etc., what does this equal?
Infinity.
So one answer is infinity. Can anybody give me another answer?
Isn't there like
Zero.
some like
Not
Oh,
zero, but you're
there's
off
like
by
some
1.
silly like Ramanujan trick
Yeah.
about this where
It's
I sort
not
of forgot.
it's not 0. It's close to 0.
It's
One
some
over
kind of
two.
negative 1/12 or something.
No, it's not negative 1/12.
That's the sum of the that's like the sum of the natural
Yeah,
numbers,
that's
but yeah.
That's the sum of all the integers.
Yeah.
1 over 2? No.
Not 1 over 2. You're close.
Negative 1 over 2?
No, just negative 1.
Oh.
Why is this
Are we
negative
talking
1?
about like p-adics?
So theoretically, it is true. So if you've seen the p-adics, this is true. This is because it's a geometric series with r equals 2. So you get 1 over 1 minus 2, which is negative 1.
Oh.
Now, can you use the geometric series when r equals 2? No. But we can somehow interpret this. And so what we mean is that the series 1 plus x squared plus x cubed plus dot 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 dot, it has some connection to 1 over 1 minus x. This is okay if the absolute value of x is less than 1. This is okay if x does not equal 1. So this is called a continuation of the left-hand side. So what this means is when they both exist, they agree. So the same when the absolute value of x is less than 1, but defined for more x. We've seen this with the gamma function and the factorials. So I'm taking a function which is initially defined in one region and extending it to be defined elsewhere. Okay? I do not mean that the sum of the powers of 2 is equal to -1. But there is a way to interpret that, that process really does look like -1. If you've seen the two adducts, there is a connection. I'm happy to talk about that if people are interested. There's enough to do today that I don't want to take that much of a digression, but there is a tremendous amount going on in the background. So this is one of the big topics. This is called, analytic continuation. So we start off with a function that exists in one region, and we come up with a new function that exists for more values and agrees with the original function when they're both defined. Okay? So now, can anybody give me the movie with the quote, "Do you believe in unlikelihoods?" This is the cultural extra credit for today.
I think I forgot.
The image from earlier today was from the movie Miracle. This is from a related movie, but more of a comedy. All right, no one gets the cultural extra credit for today. All right, so I'm going to define the function theta to be the sum of e to the negative pi n squared x. And it turns out I can define a related function to be theta of x minus 1 over 2. Well, that's really easy to do. Subtract 1, divide by 2. If I subtract 1, I'm basically removing the n equals 0 term. So this removes n equals 0 and now counts plus n and minus n as one term. So because I'm dividing by 2, the contribution from n equals 5 and the contribution from n equals -5, well, it's the same contribution because it's only a function of n squared. I'm just replacing it. Why do I care about this function? It turns out this function has some incredible properties. Theta of 1 over x is x to the 1/2 theta of x, if x is greater than 0. Or once you know how theta transforms, you can figure out how omega transforms. And so it's a nice exercise. If you know how theta transforms, prove that omega of 1 over x is -1/2. I don't know why I wrote plus -1/2 x to the 1/2 plus x to the 1/2 omega of x. So we will see a proof of this later in Fourier analysis. So we'll prove in Fourier analysis. Right now, we are going to just assume that this identity holds. And from this identity, we're going to deduce some wonderful properties of the Riemann-Zeta function. And then we'll see how the Riemann-Zeta function is connected to counting things on primes. And then hopefully this will motivate now why we want to study Fourier analysis. Because Fourier analysis gives us wonderful relationships like this. So the first question, whenever I give you something like theta, is you always have to ask, does theta exist? So is theta of x well defined? Well, we have, I could look at theta of x, or I could look at omega of x, doesn't really matter. And so omega of x is the sum, and goes from 1 to infinity, of e to the negative pi n squared x. And this is going to be less than equal to the sum, and goes from 1 to infinity, of e to the negative pi n x to the n. Actually, this is more than just less than equal to, this is just equal to, right? I've just pulled out an n. But this is the same as less than equal to n goes from 1 to infinity, e to the negative pi x to the n. Because when n is greater than 1, it makes the number smaller. So if I just replace the inside with n equals 1, I'm only making things larger.
Do we assume x to be greater than 0?
So we're assuming x to be greater than 0.
Okay.
And if you look, over here, we say we're only considering things when x is greater than 0. So does this sum converge?
Yes.
Why?
Yeah.
Geometric series.
Good. It's a geometric series. And the ratio is e to the negative pi x, which is less than 1. If x equals 0, trouble. Because then e to the negative pi times 0 is 1. So if x is 0, there's trouble. As long as x is positive, everything is okay. Think of polar coordinates. Think back to Math 150. The polar coordinates break down at 1 point, right? You no longer have a unique one-to-one onto map. Can we still use polar coordinates and do a lot of integrals? Yeah. The fact that it breaks down at 1 point is not a big deal. Okay? If it broke down at multiple points, we could have trouble. But at 1 point, it's fine. Okay, so now what we want to do is we want to come up with another expansion for the Riemann zeta function. And so we start off with the gamma function. So the gamma function is the integral from 0 to infinity, e to the negative t, t to the s minus 1 dt. And I claim that this implies that this integral is gamma of s halves over n to the s pi to the s halves. And why do we care? Well, so if we sum over n, what would we get? So we want to sum this expression over n. So it turns out if we sum over n, this e to the negative n squared pi x, does that look familiar?
Theta x?
Yeah, it's actually going to be omega of x, because we're only going to go from 1 to infinity.
Oh, yeah, yeah.
So we would get the integral from 0 to 1 of x to the 1/2 s minus 1 omega of x dx. And the right-hand side, when we sum this, it's going to be gamma of s halves pi to the negative s halves zeta of s. So if there's an equality here, we can now connect zeta of s to an integral of omega of s. So this connects zeta of s to an integral of omega of x. And so we just have to prove the claim.
Oh, so in the integral, why did we write from 0 to 1 instead of from 0 to infinity?
Oh, sorry. That should be 0 to infinity. Sorry.
Okay.
Later on, we're going to integrate from 0 to 1. So to prove the claim, we basically do some change of variables. So I'll let you do the algebra. So we can send e to the minus t to e to the minus n squared pi x by, t equals n squared pi x. So dt would be n squared pi dx. And so then we would get n to the minus s pi to the negative s halves integral x goes from 0 to infinity e to the negative n squared pi x n squared pi x to the s halves minus 1 n squared pi dx. And so we just keep playing some games and doing some algebra, and we would get n to the minus s pi to the minus s halves n to the s pi to the s halves integral x goes from 0 to infinity e to the negative n squared pi x x to the s halves minus 1 dx, and this part over here is just going to be 1. So if you just go through the algebra, it's not surprising that this is going to come out equaling what we said with the gamma and the s's. Okay, so now for the last part today, bring the pieces together. So we now have this connection. We know that pi to the minus 1/2 to the s gamma of s halves zeta of s is equal to this integral of omega. So we know this nice thing, pi to the minus 1/2 s gamma of s halves zeta of s is the integral from 0 to infinity of x to the 1/2 s minus 1 omega of x. And we know omega of x and omega of 1 minus x are related. So the rest is going to just be some algebra. So when I look at the integral from 0 to infinity, I claim we should split the integral from 0 to infinity with a really good point. Where should we integrate to?
Well, you said earlier that we integrate from 0 to 1.
Yeah, I slipped up because I knew what was coming.
You spoiled it.
I know. It's been a long night. I was up till 5:30 with my daughter. So we integrate from 0 to 1. And the reason is over here, we can have this as omega of x. And then over here, we have omega x, but now we change variables. So how should we change variables? What should be the relationship between t and x?
1 over x.
1 over x. And so then dt would be negative 1 over x squared times dx, or dx would be negative x squared, which is negative, I think, t to the minus 2 dt. And then as x goes from 1 to infinity, what does t go from?
0 to 1.
1 to 0.
1 to 0.
Oh, 1 to 0.
But then the minus sign lets us go from 0 to 1.
Hmm.
So what happens is this integral just stays the same, 0 to 1 of, x to the 1/2 s minus 1 omega of x. And now we're going to get another integral from 0 to 1 of, x to the 1/2 s minus 1 times something with, omega to the 1 over x plus other stuff. Oops. It seems like the next slide did not transfer. So when the dust settles, I'll put it in the correct order later, we get pi to the negative 1/2 s gamma of s halves zeta of s. This is just doing the algebra, is 1 over s minus 1 plus the integral. Oh, I'm sorry. So instead of doing things from 0 to 1, I want to do things from 1 to infinity. X to the 1/2 s minus 1 plus x to the negative 1/2 s minus 1/2 omega of x dx. And actually, it should be clear that this was a bad way to do things. Why is this bad? Why is it bad to go from 0 to 1? Omega x blows up
Oh, yeah.
as x goes to
Near
0.
Mm.
Go from 1 to infinity. So really, the integral from 1 to infinity keep, and the integral from 0 to 1, switch that to an integral from 1 to infinity. That's the only thing that you have to do differently. That's where you make the change, not from 1 to infinity, but from 0 to 1, because omega blows up near 0, so do it the other way. Now you have wonderful decay properties. And so now if you look at what's going on, this is a fixed piece. You see the pole at s equals 1. Over here, this has incredible decay. For x greater than or equal to 1. So this integral is well defined for all s. And we see that if we replace s with 1 minus s, it is unchanged. And so this gives us a continuation of the zeta function. So we can now continued zeta of s to all s, and the values at s and 1 minus s are the same if we multiply by factors. And so this is a good continuation to look at. All right, so this is a good place to stop. I'll stay online for a few minutes in case anybody has any questions.